Gently close your eyes, breathe softly, and let your mind drift. Have you ever truly paused to wonder, beyond what our senses tell us, what reality itself is fundamentally made of? Is it solid matter, ceaseless energy, a cosmic dream, or perhaps a hidden code? What unseen foundation underpins every leaf, every star, every thought you've ever had? What if the universe's deepest secret is woven into the very fabric of existence, waiting for us to quietly contemplate its true nature? Hello there, and welcome to Sleepster, your cozy corner of curiosity where the profound mysteries of the cosmos come with a side of serenity. Whether you're winding down after a long day, perhaps tucked under blankets with your phone propped against a pillow, its soft glow a familiar comfort, or simply letting your mind float gently towards sleep, easing its way into the quiet currents of the night, I'm so glad you're here. Tonight, we're setting our sights on the ultimate cosmic enigma, exploring the astonishing silent alchemy of what reality is truly made of. From the elusive dance of subatomic particles to the grand, unified tapestry of consciousness itself. This is the story of the universe's most fundamental secret, a marvel that defines your very perception of existence. Now, I must confess, I do hope this video isn't too fascinating. After all, the goal is to help you drift off peacefully. But if you do find yourself wide-eyed at the wonder of existence's hidden layers, captivated by the intricate processes that forge your very perception of reality, well, at least you'll be wide-eyed and a little wiser. Before we delve into the hidden architecture of the cosmos, I'd love to know, where in the world are you listening from tonight? What time is it where you are? Feel free to leave a comment and say hello. It's always such a joy to see this sleepy little community stretch across time zones and continents, a quiet constellation of curious minds connected by the shared space of contemplation. If you find comfort in videos like this, equal parts knowledge and calm, a gentle tap on the like button or a quiet subscribe helps more than you know. It's a small action that supports hours of research, writing, and a whole lot of softly whispered wonder, allowing this peaceful channel to reach more minds seeking serenity. And just before we begin, a quick reminder. While this video is full of intriguing science and captivating philosophical questions about the cosmos and consciousness, it's not medical advice. If you're struggling with sleep regularly or with persistent thoughts that cause distress, it's always best to speak to a qualified professional. This video is here to relax, to ignite wonder, and to gently guide your mind, not to replace professional care. All right, let's settle in. Take a breath and begin our gentle journey into the heart of reality's deepest enigma. We're not seeking to definitively solve the entire mystery of what reality is tonight, but rather to serenely explore its many facets, from the fundamental particles that dance within us to the grand, unified tapestries of space-time, consciousness, and perhaps even cosmic dreams. Imagine everything you see, feel, and think. The chair you sit on, the air you breathe, the warmth of a memory. How does such a seemingly tangible world manifest from what science increasingly tells us are empty space? Quantum probabilities and vibrating fields. What are the underlying mechanisms, the hidden processes, the secret alchemy that transforms the raw stuff of existence into the conscious world you inhabit? As we explore, allow your mind to drift through the currents of possibility, embracing the calm curiosity that comes with contemplating the profound and deeply personal unknown of our own inner universe and the boundless cosmos that contains it. In our everyday waking lives, reality presents itself with an undeniable sense of solidity, of tangibility, of an objective existence independent of our minds. The ground beneath our feet feels firm. The objects we touch possess definite shapes and textures, and the air we breathe seems to fill the space around us with a continuous presence. This intuitive perception forms the very bedrock of our experience, allowing us to navigate the world with effortless confidence, assuming that what we see and touch is precisely what is there. Yet, beneath this comforting veil of apparent solidity, modern physics reveals a truth far stranger, far more ephemeral, and infinitely more profound than our senses can possibly convey. What if this very solidity, this pervasive sense of tangibility, is in fact a magnificent illusion, meticulously constructed by our brains from underlying components that are anything but solid? This section invites us to gently peel back the layers of everyday perception, moving beyond what our senses tell us, to contemplate the astonishing reality that lies beneath the surface of appearances, questioning the very bedrock of what we believe to be real and revealing. How the universe is composed of far more wonder than meets the eye. Let us begin our gentle descent into the heart of this illusion by revisiting the seemingly simple concept of matter. From a macroscopic perspective, a rock is undeniably solid, a table is firm, and a human body feels dense. However, as we zoom in, layer by meticulous layer, physics unveils a vastly different picture. If we could shrink ourselves down to the size of an atom, we would discover that what appears to be solid is in fact almost entirely empty space. An atom, the fundamental building block of all matter, is composed of a tiny, incredibly dense nucleus surrounded by a cloud of even tinier, rapidly orbiting electrons. If the nucleus of an atom were the size of a pea, the nearest electron would be kilometers away. This means that the vast majority of an atom's volume is nothing but empty space. The apparent solidity of matter, then, arises not from atoms, being physically packed tightly together like tiny billiard balls, but from the powerful electromagnetic forces between the negatively charged electrons of one atom and the negatively charged electrons of another. These forces create a repulsion that prevents atoms from truly passing through one another. When you touch a table, you're not actually making physical contact with its atoms. You are feeling the electromagnetic repulsion between the electrons in your hand and the electrons in the table, creating the sensation of solidity. This fundamental emptiness at the atomic level is the first, most striking revelation about the illusory nature of what we perceive as solid matter transforming our understanding from rigid blocks to dynamic fields of force. This journey into the subatomic reveals even stranger truths. The electrons, protons, and neutrons that constitute atoms are not simple, solid particles either. Quantum mechanics is a perplexing but incredibly accurate theory that governs the behavior of matter and energy at the smallest scales, tells us that these fundamental constituents often behave not like discrete solid objects, but like waves of probability. An electron, for instance, doesn't exist at a specific point in space until it is observed. Rather, it exists as a cloud of probability, a wave function describing the likelihood of finding it at various locations. This dual nature, where particles can also act as waves, fundamentally challenges our classical intuition of distinct, tangible objects. Furthermore, these subatomic particles are not static. They are in constant, furious motion, vibrating, spinning, and exchanging influence in ways that defy our macroscopic experiences. The very notion of a solid, unchanging thing dissolves into a dynamic dance of energy, probability, and fleeting interactions. What we perceive as a stable, solid object is, in essence, a vast collection of these tiny, buzzing, vibrating, and largely empty systems, held together by incredibly strong fundamental forces that operate across vast atomic voids. The energy that binds these seemingly empty atoms and their constituent particles together is immense, further emphasizing the dynamic nature of reality. Einstein's famous equation, E equals mc, eloquently demonstrates that mass and energy are interchangeable. Mass can be converted into energy, and energy into mass. This means that the stuff of reality, at its most fundamental level, is not inert matter, but a form of congealed energy continuously vibrating and interacting. The very forces that make an atom appear solid to us are manifestations of this underlying energy, A strong nuclear force binds quarks into protons and neutrons. And the electromagnetic force binds electrons to nuclei and atoms to each other. These forces are not just abstract concepts. They are the active, dynamic glue of the universe, constantly at play, creating the illusion of a static structure from ceaseless energetic motion. When we look deeply enough, what we call matter is really just highly organized patterns of energy and force swirling in vast fields of emptiness, a profound testament to the universe's energetic and elusive nature. Our senses, finely tuned by evolution to navigate a medium-sized world, are inherently limited in their ability to perceive this deeper reality. We perceive solidity because our sensory systems are built to interact with electromagnetic forces at the macroscopic level. Our eyes detect specific wavelengths of light. Our ears detect vibrations within a narrow frequency range. And our touch receptors respond to the repulsion of electron clouds. These senses provide us with a highly useful, simplified model of reality user interface that allows us to survive and thrive in our physical environment. However, this interface intentionally filters out the chaotic quantum dance, the vast emptiness, and the raw energy that truly constitute matter. The brain, our master constructor, then takes these filtered sensory inputs and builds a coherent, stable, and surprisingly robust inner world, filling in the gaps and making sense of the otherwise overwhelming flood of raw data. This is why optical illusions work so powerfully. They demonstrate how the brain actively interprets, rather than passively receives, sensory information, proving that our perception is a construction, not a direct window. The solidity we feel, then, is a brilliant, necessary illusion, a cognitive shortcut that allows us to function efficiently without being overwhelmed by the true quantum complexity of the universe. The implication that reality is not what it seems extends beyond the physical makeup of matter to the very nature of existence. If everything is fundamentally energy and empty space, what are we truly interacting with? This question opens the door to philosophical contemplation. Is reality fundamentally physical, but our perception of it is limited? Or is reality itself more abstract, perhaps fundamentally made of information or consciousness, with the physical world merely being a manifestation or projection of these deeper principles? The illusion of solidity challenges our materialistic assumptions, inviting us to consider that the universe might be far more subtle, interconnected, and dynamic than our everyday senses reveal. It encourages us to look for the hidden patterns, the unseen forces, and the underlying truths that govern existence, leading us to question the very bedrock of what we assume to be real. This profound contemplation of the vast emptiness and ceaseless energy that lie beneath the surface of all things can be deeply calming. It allows us to release our rigid adherence to what appears to be and to embrace a more fluid, wondrous, and mysterious understanding of the reality we inhabit. In the quiet moments of contemplation, the illusion of solidity gently dissolves, leaving behind a pervasive sense of wonder for the universe's elegant, hidden dance of energy and potential. Having gently begun our profound inquiry into what reality is truly made of, peeling back the comforting illusion of solidity to reveal a universe that is mostly empty space, held together by unseen forces and swirling energy, we now descend even deeper. Our contemplative gaze turns to the most bewildering, most paradoxical, and ultimately most fundamental realm known to science, the quantum riddle. This is the domain of quantum mechanics, the perplexing yet incredibly accurate theory that governs the behavior of matter and energy at the atomic and subatomic scales, revealing a truth so profoundly strange that it defies our everyday intuition. Where particles become waves, certainty dissolves into probability, and observation itself can seemingly shape reality. Imagine a world where a single entity can be In two places at once where particles are intrinsically linked across vast distances, and where the very act of looking at something changes what it is. This section invites us to calmly embrace this deep strangeness, to explore the bizarre phenomena of the quantum realm, and to contemplate what these profound paradoxes tell us about the true, elusive nature of the reality we inhabit, fostering a deeper, more serene appreciation for the universe's hidden, fundamental complexities at its core. Quantum mechanics is the scientific framework developed in the early 20th century to describe the behavior of matter and energy at scales so minuscule they are beyond direct human perception, the realm of atoms, electrons, photons, and quarks. It emerged because classical physics, the laws that brilliantly describe the motion of planets or the trajectory of a thrown ball, utterly breaks down when applied to these tiny entities. In the quantum world, particles do not behave like miniature billiard balls with precise positions and speeds. Instead, they operate according to rules that seem utterly alien to our macroscopic experience. Despite its inherent weirdness, quantum mechanics is perhaps the most successful scientific theory ever conceived, providing incredibly precise predictions that have been verified by countless experiments, forming the bedrock of modern technology, from lasers and transistors to computer chips and medical imaging. Yet, its philosophical implications continue to profoundly shock and mystify even the most seasoned physicists. Niels Bohr, one of the pioneers of quantum theory, famously remarked, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. This inherent strangeness is not a flaw in the theory. It is a fundamental property of reality itself, a quantum riddle that ceaselessly challenges our most basic assumptions about how the universe works." One of the most foundational and perplexing aspects of the quantum riddle is wave-particle duality. In our everyday world, objects are either particles discrete, localized entities like a grain of sand, or waves spread out, continuous disturbances like ripples on a pond. But at the quantum level, entities like light and even matter itself defy this clear distinction. The history of light provides a perfect illustration. For centuries, scientists debated whether light was made of tiny particles, Newton's corpuscular theory, or continuous waves, Huygens wave theory. Thomas Young's famous double-slit experiment in the early 19th century provided compelling evidence for light's wave-like nature. When a beam of light passes through two narrow slits, it creates an interference pattern of bright and dark bands on a screen identical to what you would see if water waves passed through two openings. This seemed to definitively prove light was a wave. However, in the early 20th century, Albert Einstein's explanation of the photoelectric effect, how light knocks electrons off metal surfaces, demonstrated that light also behaves as discrete packets of energy called photons, acting like particles. The paradox deepens when you observe electrons, traditionally thought of as particles with mass. Louis de Broglie hypothesized that particles like electrons also possess wave-like properties, and later experiments, such as electron diffraction, confirmed this astonishing fact. Electrons, when fired at a double slit, also produce interference patterns behaving like waves. So the quantum riddle presents us with a profound paradox. How can something be both a localized, discrete particle and a spread-out, diffuse wave at the same time? The answer seems to be that it is neither or both, depending on how we look at it. This schizophrenic nature of quantum reality forces us to abandon our intuitive, classical notions of what constitutes a fundamental thing and suggests that reality is far more fluid and ambiguous at its most basic level, always existing as a superposition of possibilities. Having gently delved into the profound quantum riddle, exploring the bizarre paradoxes where particles become waves, and certainty dissolves into probability, revealing that reality is far from solid at its most fundamental level. We now turn our contemplative gaze to another equally mind-bending, yet profoundly elegant, revolution in our understanding of existence. We embark on a journey into the very fabric of spacetime, guided by the luminous insights of Albert Einstein. To comprehend how gravity is not merely an invisible force pulling objects down, but rather a profound active bending of reality itself. Imagine the familiar vastness of space and the relentless march of time, not as separate, rigid backdrops against which events unfold, but as a single, dynamic, and incredibly elastic tapestry. A cosmic stage that is continuously stretched, warped, and influenced by the presence of matter and energy. This section invites us to calmly embrace this grand perspective, to explore how Einstein's theories of relativity fundamentally reshaped our understanding of space, time, gravity, and ultimately, what reality is truly made of, fostering a deeper, more serene appreciation for the universe's hidden, flexible dimensions. For centuries, our intuitive understanding of space and time was profoundly shaped by the classical physics of Isaac Newton. In Newton's grand mechanistic universe, space was an absolute, unchanging, three-dimensional stage-up, vast, rigid, invisible grid that existed independently of anything within it. Time, equally absolute, was conceived as a universal clock, ticking uniformly and relentlessly forward, ticking at the same pace for everyone, everywhere, entirely independent of events or observers. Gravity was merely a mysterious force, an invisible pull exerted instantaneously between massive objects, without any clear explanation of how that pull propagated across vast distances. This Newtonian view, while incredibly successful for describing everyday phenomena and the motion of planets, presented a picture of reality as a static, fixed backdrop. A stage upon which the drama of the universe played out, but a stage that itself remained unaltered by the actors or their actions. It was a simple, elegant, and profoundly influential conception, providing comfort in its absolute predictability, but it was a picture that would soon be profoundly and beautifully challenged by a mind daring to question the very foundations of existence. The first crack in this Newtonian edifice emerged in 1905 with Albert Einstein's special theory of relativity. This groundbreaking theory began with two deceptively simple, yet revolutionary postulates. The first states that the laws of physics are the same for all observers in uniform motion, regardless of their constant velocity. The second, and perhaps most mind-bending, asserts that the speed of light in a vacuum is constant for all observers, regardless of the motion of the light source or the observer. This single, unwavering speed limit for light, often denoted as c, became the ultimate cosmic constant. The consequences of these postulates are astonishing, fundamentally intertwining space and time in ways previously unimaginable. One of the most famous implications is time dilation, the phenomenon where time actually slows down for objects moving at very high speeds relative to an observer who is at rest. Imagine a cosmic clock, perhaps a beam of light bouncing between two mirrors. For an observer moving incredibly fast past this clock, the light has to travel a longer, diagonal path to reach the mirrors, yet its speed remains constant. The only way this is possible is if time itself slows down for the moving clock. This isn't an illusion. It's a measurable physical reality. Subatomic particles, called muons, which have very short lifespans, are created high in Earth's atmosphere. They decay almost instantly. But muons traveling near the speed of light from cosmic rays reach Earth's surface before decaying, because, for them, time has slowed down, extending their perceived lifespan. A profound piece of empirical evidence for time dilation. Further, implications of special relativity include length contraction, where objects moving at extremely high speeds appear to become shorter in the direction of their motion, as perceived by a stationary observer. A spaceship traveling near light speed would appear flattened along its direction of travel. And perhaps most famously, special relativity gave us the iconic equation E equals mc, revealing the profound equivalence of mass and energy. This equation demonstrates that mass is simply a highly concentrated form of energy, and energy can be converted into mass and vice versa. This insight fundamentally redefines what matter is made of, showing that what we perceive as solid stuff is merely a manifestation of immense congealed energy. The intertwining of space and time, the relativity of measurements, and the equivalence of mass and energy all pointed to a deeper truth. Space and time are not separate entities, but rather components of a unified, four-dimensional fabric called spacetime. This revolutionary concept, first mathematically formulated by Hermann Minkowski, implies that every event in the universe occurs at a specific point in this four-dimensional space-time continuum, and our perception of space and time depends on our motion through this unified fabric, making reality itself far more dynamic and interconnected than previously imagined. While special relativity brilliantly described how space and time are relative to motion, it did not fully explain gravity. That monumental task fell to Einstein's general theory of relativity, published in 1915, which transformed our understanding of gravity from a mysterious force into a manifestation of the geometry of space-time itself. General relativity began with the principle of equivalence, which states that the effects of gravity are completely indistinguishable from the effects of acceleration. Imagine being in a windowless elevator. If you feel a push pinning you to the floor, you cannot tell if it is due to gravity pulling you down or the elevator accelerating upwards. This simple yet profound insight allowed Einstein to bridge gravity with the geometry of space and time. He proposed that gravity is not a force, as Newton had thought, but rather the curvature or warping of space-time caused by the presence of mass and energy. Imagine space-time not as a rigid, flat stage, but as a vast, pliable rubber sheet. When you place a heavy bowling ball representing a star or a planet on this sheet, it causes the sheet to dip and curve. Now, if you roll a marble representing a smaller planet or a beam of light nearby, it doesn't get pulled by the bowling ball. Instead, it simply follows the curvature created by the bowling ball's mass, appearing to orbit or bend towards it. In the same way, planets orbit, stars, and light bends around massive objects. Not because of a mysterious gravitational pull, but because they are simply following the curves and dips in the space-time fabric created by those massive objects. The consequences of gravity as space-time curvature are even more astonishing, revealing a universe that is truly dynamic and elastic. One of the most direct implications is gravitational time dilation. Time ticks slower in stronger gravitational fields, meaning clocks tick more slowly closer to massive objects. For instance, a clock at sea level ticks infinitesimally slower than a clock at the top of a mountain, where gravity is slightly weaker. This effect, though minuscule on Earth, is crucial for technologies like GPS satellites. Their clocks tick slightly faster than clocks on the ground because they are in a weaker gravitational field, and without precise relativistic corrections. GPS systems would quickly accumulate errors, demonstrating that time truly bends under the influence of gravity. Observational evidence for general relativity is abundant. Gravitational lensing, where light from distant galaxies is bent and magnified as it passes around massive galaxy clusters acting as natural cosmic telescopes, provides stunning visual proof of space-time curvature. The first confirmation came during a solar eclipse in 1919, when Arthur Eddington observed starlight bending around the sun. More recently, the direct detection of gravitational waves in 2015. ripples in spacetime itself caused by extremely energetic cosmic events like the merger of black holes or neutron stars, provided the ultimate confirmation of general relativity's profound insights, allowing us to hear the very vibrations of spacetime for the first time. The most extreme manifestation of spacetime curvature is the concept of black holes. These cosmic behemoths are regions of spacetime, where gravity is so incredibly strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. Inside the event horizon, spacetime is so profoundly warped that all paths lead inevitably towards a single point of infinite density, a singularity. From an outside observer's perspective, time itself appears to slow down for objects falling into a black hole, stretching infinitely as they approach the event horizon before vanishing from our observable universe. The very notion of time and space, as we understand them, breaks down within these enigmatic cosmic entities, representing the most dramatic testament to the elastic and dynamic nature of reality's fabric. Black holes are not just cosmic vacuum cleaners. They are profound laboratories where the laws of physics are pushed to their absolute limits, compelling us to reconsider the very nature of existence. The cumulative implications of special and general relativity for what is reality truly made of are profound and transformative. Firstly, reality is not a static backdrop, but a dynamic, active participant, continuously being shaped by the presence of matter and energy. Secondly, time and space are not separate, fixed entities, but fluid, interconnected components of a unified spacetime fabric that can stretch, compress, and warp. Thirdly, matter and energy are deeply intertwined and possess the astonishing ability to bend the very geometry of existence. Fourthly, gravity is not a mysterious force, but an elegant manifestation of this geometric curvature. The universe, in this relativistic view, is a constantly warping, flowing entity, a cosmic dance where everything is interconnected in a dynamic space-time ballet. Philosophically, these insights lead to powerful contemplations. The relativity of experience implies that there is no single, universal now across the cosmos. Observers in different gravitational fields or in different states of motion will experience time differently. This challenges our intuitive sense of a shared absolute present moment and underscores the subjective nature of our temporal reality. The mathematical beauty and elegance of Einstein's equations reveal a universe that operates according to deep, underlying symmetries, inspiring a sense of profound awe. The humility of realizing how deeply intertwined space, time, matter, and energy are, and how much grander the universe is than our initial assumptions, can be a source of immense peace. The cosmic neuron analogy, when viewed through the lens of relativity, gains a new dimension. If space-time is the fundamental fabric of the universe, the very body of this cosmic neuron, how does its bending and warping relate to a cosmic mind's activity? Could a cosmic thought be a precise curvature of its own spacetime? Could the flow of cosmic information literally bend the geometry of its own brain? This suggests a profound and dynamic relationship between mind, matter, and spacetime itself, where the physical form and the conscious process are inextricably linked, inviting a serene acceptance of the universe's elegant, hidden beauty. Having gently journeyed through the mind-bending complexities of quantum mechanics, where particles dance as waves and certainty dissolves into probability, and having explored how the very fabric of spacetime bends and warps under the influence of gravity, revealing a dynamic and elastic reality, we now turn our contemplative gaze to an even more abstract, yet profoundly fundamental, layer of existence. We delve into a bold and captivating hypothesis. What if reality, at its deepest core, is not fundamentally made of matter or energy, but of information itself? This is the essence of the digital universe hypothesis, a profound shift in perspective that suggests reality might operate like an immense, intricate computation, its fundamental laws akin to algorithms, and its constituents more like bits of data than solid objects. Imagine the universe not as a collection of things, but as a ceaseless flow of interconnected information, constantly being processed and updated, its patterns forming the very world we perceive. This section invites us to calmly explore this radical idea to understand what information truly means in a cosmic context, and to contemplate the astonishing possibility that our reality might be a grand, unfolding cosmic program, fostering a deeper, more serene appreciation for the universe's hidden informational dimensions. To truly grasp this profound concept, we must first gently redefine what information actually is in this context, moving beyond its everyday usage. In common parlance, information refers to data, facts, or news. However, in the realm of physics and philosophy, information takes on a far more fundamental meaning. Here, information refers to the fundamental patterns, organization, and distinctions within a system. It's about what defines a state, what distinguishes one particle from another, what gives structure to the cosmos. It's not merely about reality, it is reality. This perspective is perhaps best encapsulated by physicist John Wheeler's famous adage, "It from bit." Wheeler proposed that every physical it, every particle, every field, every law derives its existence from the answer to a yes or no question, a binary choice, a bit of information. This suggests that information in its most elementary form might be more fundamental than matter or energy, forming the very bedrock of existence. The groundbreaking work of Claude Shannon in classical information theory, which quantifies information in terms of bits and entropy, a measure of disorder or uncertainty, provides a mathematical language for understanding how information is transmitted and processed. When applied to the universe, this suggests that the laws of physics might be essentially rules for processing cosmic information, and the universe itself is a grand information system constantly updating its state. The idea that information might be fundamental to reality finds compelling resonance within the very heart of physics, particularly in the most perplexing phenomena of the quantum realm and general relativity. In quantum mechanics, as we explored earlier, particles do not have definite properties until they are measured. They exist as a superposition of possibilities. The act of measurement collapses the wave function, forcing the particle to assume a definite state. From an informational perspective, this means that before measurement, reality exists as a set of potential bits or possibilities, and the measurement reads out or decides a specific bit of information, actualizing a particular reality. Furthermore, quantum entanglement, where particles remain inextricably linked regardless of distance, hints at a profound non-local exchange of information, suggesting an underlying informational unity across vast stretches of space. The very information content of quantum states seems to be fundamental and irreducible, defying classical notions of independent, local objects. In the realm of black holes, the information paradox vividly illustrates the fundamental nature of information. Classical physics suggests that information about matter falling into a black hole is irrevocably lost, defying the laws of quantum mechanics, which state that information cannot be truly destroyed. Solutions to this paradox often involve the idea that information is somehow preserved, perhaps encoded on the black hole's event horizon, or radiated away through Hawking radiation, reinforcing information's fundamental and conserved status in the universe, placing it on par with energy and momentum. The holographic principle, a speculative but deeply compelling concept arising from black hole thermodynamics and string theory, pushes the idea of information as fundamental even further. It proposes that all the information describing a three-dimensional volume of space, like our entire universe, can be entirely encoded on its two-dimensional boundary, much like a hologram. Imagine a vast three-dimensional scene projected from a flat two-dimensional surface. If this principle holds true for the universe, it means that our entire three-dimensional reality, with all its depths and complexities, might fundamentally be a holographic projection from a distant, two-dimensional, cosmic boundary. This idea profoundly challenges our intuitive understanding of dimensionality and reality, suggesting that what we perceive as a rich, volumetric physical world might, at its deepest level, be encoded as mere patterns of information on a distant surface, blurring the line between illusion and reality. These profound insights from physics give rise to the digital universe hypothesis, or digital physics, which posits that the universe is not just like a computer, but is a giant computational system, or that its fundamental laws are inherently algorithmic. Early proponents, like Konrad Zuse, the inventor of the first programmable computer, suggested that the universe's behavior is the result of a vast computation. Later, Edward Fredkin proposed the finite nature hypothesis, suggesting that the universe is a form of cellular automaton, a vast grid of simple interacting cells, each following discrete rules, which collectively give rise to immense complexity. This implies that space, time, and matter are not continuous, but ultimately discrete. Composed of fundamental pixels, perhaps at the Planck length, the smallest theoretical unit of space, approximately 1035 meters, and fundamental ticks of time, Planck time, approximately 1043 seconds. In this view, the universe is continuously computing its next state based on its current state, driven by the algorithms encoded in the laws of physics and the values of fundamental constants, which act as the universe's code. Stephen Wolfram's work on cellular automata and computational irreducibility further explores how incredibly simple rules can generate seemingly infinite complexity, suggesting that the intricate universe we see could arise from very basic, underlying computational processes akin to a complex software program running on ultimate cosmic hardware. The motivations for considering information as fundamental are compelling. Firstly, it offers a potential way to unify quantum mechanics and general relativity, two powerful theories that currently describe different aspects of reality but are difficult to reconcile. If reality is fundamentally information, perhaps there's a common informational language that both theories can speak. Secondly, it provides an elegant explanation for the apparent precision and elegance of the universe's fundamental laws and constants. If the universe is a program, its laws are simply the code, and its constants are the parameters that define the computation, perhaps set by a cosmic programmer. Thirdly, it offers a novel perspective on the very nature of existence. Instead of trying to understand what particles are, we can focus on what information they contain and how they process it, shifting the focus from substance to function. This allows us to envision the universe as a dynamic, evolving computation, constantly updating its own state based on an underlying, intrinsic, algorithmic nature, making it a living, thinking, data processing entity on an unimaginable scale. The implications of information is reality for consciousness and existence are deeply profound, echoing some of our previous contemplations on the cosmic neuron hypothesis. If reality is fundamentally information, then our own brains are extraordinarily complex information processing systems. Consciousness, in this view, could be an emergent property of sophisticated information processing, a highly intricate algorithm running on the neural hardware of the brain. Our thoughts, feelings, and perceptions would then be unique patterns of processed information, forming our subjective reality. Extending this, if the entire universe is a giant cosmic computer processing fundamental information, then a cosmic mind could emerge from this universal computation. This cosmic mind would not be biological in our sense, but a vast, distributed intelligence processing cosmic information over astronomical timescales. Our universe, as a brain cell in this context, would be a highly specialized subroutine or a single complex data point within this grand cosmic computation. Our individual thoughts, then, might be seen as tiny, localized computations or data points contributing to the larger, ongoing processing of the cosmic mind. This profound connection between computation, information, and consciousness suggests that awareness might be an inherent property of organized information, regardless of scale, making our own existence a conscious data point in a universal program. The universe, in this view, is not just a stage for life, but perhaps a living, thinking entity, its thoughts being the very unfolding of reality. The philosophical reflections arising from the actual universe hypothesis offer a unique sense of comfort in data and the profound beauty of pure logic. Finding order and meaning in the universe's inherent informational structure can be immensely reassuring. The idea that reality is fundamentally intelligible, that its deepest secrets are encoded in a language of pure logic and mathematics, can foster a sense of serene understanding even if the complexity of the code remains beyond full human grasp. It implies a universe that is fundamentally rational, predictable at its core, even if its emergent properties are chaotic or mysterious. The elegance of mathematical laws, the precision of information processing, and the consistency of cosmic algorithms become the ultimate language of reality, revealing a universe that is fundamentally orderly and deeply interconnected through its informational fabric. This perspective can lead to a quiet peace, a sense of belonging to a cosmic system that, despite its vastness, is governed by coherent, beautiful principles that resonate with our own capacity for logic and understanding. Our existence, then, as conscious data points in this universal program is not arbitrary, but rather an intricate, meaningful part of an ongoing cosmic computation, inviting us to contemplate the profound beauty and inherent intelligibility of a universe made of information. Having gently journeyed through the mind-bending complexities of quantum mechanics, where observation seems to pull reality from a mist of probabilities, and having contemplated the profound idea that reality might fundamentally be information, we now embark on an even more radical and deeply introspective journey. Our contemplative gaze turns to an ancient yet profoundly resonant philosophical perspective. What if reality, in its most fundamental essence, is not material at all, but rather fundamentally mental or mind-dependent? This is the core tenet of philosophical idealism, a school of thought that posits that what we perceive as the external, physical world, the tangible chair you sit upon, the vast expanse of galaxies, the ceaseless march of time are not ultimately independent mind-external entities, but are instead manifestations of consciousness, ideas, or thought itself. Imagine for a moment that your entire existence, every sight, sound, and sensation is akin to a grand, intricate dream being experienced by a vast, universal consciousness, and your individual mind is but a unique facet of this greater awareness. This section invites us to calmly explore this profound notion, to understand its ancient roots and modern interpretations, and to contemplate what it means for the true nature of reality, bridging the seemingly disparate realms of inner experience and cosmic existence, fostering a deeper, more serene appreciation for the universe's hidden mental dimensions. To truly grasp the profound implications of idealism, it is crucial to understand its core tenet by contrasting it with its conceptual opposite, materialism or physicalism. Materialism posits that reality is fundamentally physical. Matter and energy are the primary constituents of the universe, and mind, consciousness, and thought are emergent properties that arise solely from the complex organization of physical matter, such as the brain. In this view, the universe would exist even if no mind were there to perceive it. Idealism, however, flips this paradigm. It asserts that mind, or consciousness, is primary, existing as the fundamental ground of all being. What we perceive as the physical world is then understood as a manifestation, a product, or a construct within consciousness, rather than an independent entity existing outside of it. This doesn't mean that your personal, individual mind is creating the entire universe. That extreme view is known as solipsism, only my mind exists, which is generally not what philosophical idealism proposes. Instead, idealism typically posits a more universal objective, or absolute mind or consciousness as the ultimate reality, with individual minds being unique expressions or participants within this greater whole. This radical redefinition of reality's fundamental nature compels us to question our most deeply ingrained assumptions, inviting a liberating shift in perspective from a universe of inert matter to a universe of living thought. The roots of philosophical idealism stretch back to antiquity, resonating across diverse cultures and intellectual traditions. In ancient Western thought, Plato's theory of forms can be seen as an early form of idealism. Plato argued that the physical world we perceive through our senses is merely a shadowy imitation of eternal, perfect, and unchanging non-physical forms or ideas which constitute true reality. For Plato, the ultimate reality was not the fleeting material world, but the immutable realm of ideas, accessible only through the mind. In the East, profound traditions like Vedanta, Hinduism, and various schools of Buddhism have long articulated sophisticated idealist metaphysics. Vedanta, particularly the Advaita Vedanta school, posits that Brahman, the ultimate reality's pure consciousness, and that the perceived diversity of the material world is ultimately an illusion maya, arising from or within this singular consciousness. Buddhist philosophy, particularly certain Mahayana schools, emphasize that all phenomena are ultimately mind-only, arising from the mind's activity. These ancient traditions, developed independently, underscore a universal human intuition that mind or consciousness might be more fundamental than physical matter, challenging our common-sense notions of an external, independent world. The modern articulation of philosophical idealism gained significant prominence with the Irish philosopher Bishop George Berkeley in the 18th century. Berkeley famously put forth the radical claim, esse est percipi, which means to be is to be perceived. He argued passionately against the existence of a material substance independent of mind. Berkeley contended that all we ever directly experience are our own sensations and ideas. We see colors, hear sounds, feel textures. These are all mental phenomena, perceptions within our consciousness. We never perceive a thing in itself beyond these sensations. Therefore, he reasoned, the very existence of physical objects consists solely in their being perceived. If a tree falls in the forest and no one is there to hear it, does it make a sound? For Berkeley, if no mind, human or divine, perceives it, it simply does not exist. To avoid solipsism, the idea that only his mind existed, Berkeley proposed that an omnipresent, eternal God's mind perpetually perceives all things, thus ensuring the continuous existence of the world even when no human mind is perceiving it. His arguments fundamentally challenged materialism, suggesting that what we consider physical reality is, in essence, a coherent and consistent collection of ideas or perceptions within a greater mind. Following Berkeley, the German philosopher Immanuel Kant developed his transcendental idealism in the late 18th century. Kant agreed with Berkeley that we do not directly perceive things in themselves noumena, but only their appearances phenomena. However, unlike Berkeley, Kant did not deny the existence of a mind-independent reality altogether. Instead, he argued that our minds actively structure and organize our perceptions through innate categories of understanding, such as space, time, causality, and substance. We don't just passively receive reality, our minds actively shape it. For Kant, space and time are not external features of reality, but rather fundamental frameworks or intuitions through which our minds experience the world. Thus, reality is fundamentally mind-dependent, not because it's a dream of an individual mind, but because its very structure and organization are imposed by the universal categories of the human mind. This means that reality, as we know it, is always already shaped by the way our minds operate. Later German idealists such as Fichte, Schelling, and most notably Hegel pushed this concept further into absolute idealism, where reality is understood as the unfolding of a single, universal, self-developing absolute spirit or mind. For Hegel, history, culture, and nature are all manifestations of this absolute mind coming to full self-awareness, transforming the universe into a grand evolving thought process. The arguments for idealism, particularly in its contemporary forms, draw fascinating support from the very frontiers of modern physics, linking it unexpectedly to the quantum realm. As we explored, quantum mechanics reveals that particles do not possess definite properties until they are observed or measured. They exist as wave functions, superpositions of possibilities. The act of observation seemingly collapses the wave function into a single definite state. If reality at its most fundamental level is indeterminate until observed, does this imply a more direct role for mind or consciousness in actualizing reality? While most physicists do not interpret this as implying human consciousness literally creates reality, the perplexing nature of the measurement problem and the observer effect resonates powerfully with idealist notions. If reality is fundamentally information, some physicists propose the it from bit idea, and information needs a mind to be processed or read out, then could mind itself be primary? This perspective suggests that the universe's fundamental nature might be closer to thought or information than to inert matter, with the physical world emerging as a coherent pattern of perception within consciousness. Rather than existing independently, the implications of philosophical idealism for the profound question, what is reality truly made of, are deeply transformative. Idealism posits that reality is fundamentally consciousness, thought, or idea. Physical objects are not independently existing things, but rather consistent patterns of perception, manifestations, or constructs within a greater mind. Matter itself, the seemingly solid stuff of the universe, is understood as a derivative, or a product of consciousness, not its cause. There is no ultimate independent stuff outside of mind. Reality is inherently mental. This provides an elegant framework for understanding how thoughts are made, because thought, in this view, is not a mysterious emergent property of matter. It is the very essence of reality itself. Consciousness is primary, and all phenomena arise from or within it. This perspective offers a potential solution to the hard problem of consciousness. If consciousness is fundamental, then the question of how it arises from non-conscious matter dissolves. Instead, we ask how specific physical forms, like brains, organize this fundamental consciousness into individual minds. This brings us directly to the profound connection between philosophical idealism and our cosmic neuron hypothesis. If the universe is a single colossal brain cell within a greater mind, then its existence is fundamentally mental, a grand thought or idea within a larger cosmic consciousness. This fits perfectly with idealism's core tenet. Our entire universe, with its billions of galaxies, its intricate laws, and its ceaseless activity, could be understood as a complex, unfolding pattern of consciousness within a universal mind. Our individual minds, then, are not separate entities, but rather sparks, facets, or localized manifestations of this larger cosmic mind, each contributing to and participating in the universal awareness. The laws of physics, from this idealist perspective, are not external, immutable rules governing inert matter, but rather the consistent patterns, the grammar or logic of this vast cosmic thought process. They are the fixed ways in which the universal mind structures its perceptions or ideas, ensuring a coherent and stable reality. The cosmic neuron hypothesis, therefore, becomes not just a fascinating analogy, but a direct and compelling illustration of an idealist universe, where the physical form of the cosmos is inseparable from its underlying mental nature. While powerful, idealism also faces various challenges and counter-arguments. The most common objection is that the existence of an external world independent of our individual minds seems undeniable. If reality only exists when perceived, what happens to the world when no one is looking? Idealists often respond by invoking a universal or divine mind that perpetually perceives all things, ensuring their continuous existence. Another challenge is to explain why different individual minds perceive a largely similar reality. Idealism addresses this by positing that individual minds are experiencing a consistent, shared reality structured by the universal mind's constant perceptions and inherent order. The problem of objective knowledge also arises. If everything is mind-dependent, how can we claim objective scientific knowledge? Idealism argues that objectivity lies in the consistency and coherence of the shared perceptions within the universal mind. Despite these intellectual hurdles, the contemplative power of idealism remains profound, pushing us to question the very nature of existence. Ultimately, embracing philosophical idealism, even as a contemplative exercise, offers a unique pathway to serenity and a deep understanding of what reality might truly be made of. It allows us to release the anxiety of inhabiting a purely mechanistic, indifferent universe and find comfort in the profound idea of inherent meaning or consciousness at the very base of all reality, the interconnectedness of all minds within. A universal mind can foster a deep sense of belonging and unity. The serenity of recognizing reality as a continuously unfolding dream or thought of a vast consciousness can be profoundly calming, dissolving the boundaries between inner and outer worlds. This perspective can foster acceptance, reduce fear, even the fear of death, as consciousness simply reintegrates or shifts forms, and deepen appreciation for the richness of subjective experience. The cosmic neuron hypothesis, viewed through this idealist lens, becomes not just a scientific curiosity, but a direct invitation to contemplate the universe as a living thought, where every moment, every star, and every conscious flicker is a cherished part of a boundless, universal dream. A profound and beautiful truth that invites us to rest gently within its grand embrace. Having gently journeyed through the profound depths of quantum mechanics, where observation seems to pull reality from a mist of probabilities, and having contemplated the radical notion that reality might fundamentally be rooted in consciousness, or idealism, we now embark on an even more audacious, yet surprisingly compelling hypothesis. Our contemplative gaze turns to the notion that our entire reality, every star, every atom, every thought, might not be physical in the way we assume, but rather an incredibly sophisticated computer simulation, a grand cosmic program running on hardware we cannot yet comprehend. This is the essence of simulation theory, a bold idea that suggests we could be living within code, our universe a vast, intricate computation, its fundamental laws akin to algorithms, and its constituents more like bits of data than solid objects. Imagine the universe not as a boundless expanse of matter and energy, but as a ceaseless flow of interconnected information, constantly being processed and updated, its patterns forming the very world we perceive, a digital dream woven by an unseen intelligence. This section invites us to calmly explore this mind-bending concept, to understand its curious arguments, its surprising connections to modern physics, and to contemplate the astonishing possibility that our reality might be a grand, unfolding cosmic program, fostering a deeper, more serene appreciation for the universe's hidden, informational dimensions. At its core, simulation theory proposes a startling premise: our perceived reality, with all its intricate details, its seemingly fundamental laws of physics, and its rich tapestry of life and consciousness, might not be the base reality or the ultimate fundamental layer of existence. Instead, it posits that we are living within a highly advanced computer simulation, meticulously crafted and run by a more technologically evolved civilization or entity that resides in a higher or base reality. This isn't akin to merely putting on a virtual reality headset and experiencing a simulated world. Rather, the entire fabric of our reality, including our physical bodies, our brains, and the very laws of physics we observe, would be part of the simulation. The beings living within its which could be us would be entirely unaware of their simulated nature, experiencing their existence as their only and true reality, indistinguishable from genuine physical existence. The theory gained significant philosophical traction with arguments like the post-human hypothesis proposed by Nick Bostrom. This argument suggests that if certain reasonable assumptions hold true, namely, that technological civilizations will eventually reach a posthuman stage with immense computing power, that such posthumans would be interested in running ancestor simulations perhaps for historical research, curiosity, or entertainment, and that the computing resources would be vast enough to run many such simulations, then it's statistically more likely that we are in one of the many simulations than in the single base reality. This probabilistic argument challenges our intuitive sense of being in original reality, inviting us to contemplate a hierarchy of possible simulated existences. The appeal of simulation theory is amplified by several compelling, albeit circumstantial, arguments that draw surprising connections to modern physics and observations of the universe. One of the most frequently cited is the remarkable fine-tuning of universal constants. The fundamental physical constants and laws of our universe, such as the strength of gravity, the mass of an electron, or the fine structure constant, appear to be incredibly precise, almost miraculously calibrated for complex structures, stars, planets, and ultimately life to exist. Even minute deviations in these values would lead to a universe devoid of complexity or consciousness. From a simulation perspective, these precise values could be interpreted not as cosmic coincidences, but as carefully chosen parameters, or settings within the simulation's code, programmed by the higher intelligence running it. This offers an elegant, if speculative, explanation for the apparent anthropic principle that the universe seems perfectly designed for life. Another powerful argument emerges from the perplexing realm of quantum mechanics, which, as we've explored, already hints at a reality less concrete than it seems. The pixelated nature of reality, suggested by the Planck length, the smallest theoretical unit of space, and Planck time, the smallest theoretical unit of time, could be interpreted as the discrete pixels or clock cycles of the simulations, underlying computational grid, representing fundamental computational limits. Furthermore, the bizarre phenomena of wave-particle duality, superposition, and the observer effect, where particles appear to exist in multiple states until observed, collapsing into a definite state upon measurement, are sometimes cited as evidence for simulation. This behavior could be explained as rendering optimizations within the simulation. The program only computes the definite state of a particle when it needs to be observed, saving computational power by not continuously rendering unobserved. Reality, much like a video game, only fully renders the parts of the world the player is currently viewing. Quantum randomness could be viewed as the output of a pseudorandom number generator, rather than fundamental indeterminacy beyond the quantum realm. The mathematical nature of the universe provides another intriguing parallel. The fundamental laws of physics are elegantly described by mathematics. The universe appears to operate according to incredibly precise mathematical equations. From a digital physics perspective, this suggests that mathematics is not just a language we use to describe reality, but perhaps the very code in which reality is written. Proponents like Edward Fredkin and Stephen Wolfram have explored concepts of digital physics and computational irreducibility, where the universe is literally a giant computer, or its fundamental laws are algorithms being executed. Simple, discrete, Computational rules, like those found in cellular automata, can give rise to immense and unforeseen complexity, suggesting that the intricate universe we see could emerge from very basic, underlying computational processes, akin to a complex software program running on ultimate cosmic hardware. This perspective emphasizes that computation is not just something we do, but potentially what reality fundamentally is. The very structure of space and time, the properties of matter, and the interactions of forces are all manifestations of this ceaseless, underlying computation. The implications of living in a simulation are deeply profound and can reshape our understanding of meaning, free will, and the nature of the simulator. If our reality is a program, does it diminish the purpose of our lives? For some, it might, leading to existential nihilism. But for others, it could enhance purpose. Perhaps our existence contributes to the simulator's grand purpose, making our lives meaningful within their context. Or perhaps the simulator is running the simulation specifically to observe the emergence of complex phenomena, including our consciousness and experiences, giving our lives a unique value as data points. The question of free will becomes particularly poignant. If our reality is coded, are our choices predetermined? Or can a simulation be sophisticated enough to support genuine free will, perhaps by allowing for emergent, unpredictable behavior within its programmed parameters? The nature of the simulator itself is another layer of profound mystery. Who or what are they? Are they conscious? What are their motives? Are they scientists, gods, or simply children playing a grand game? Are they subject to their own laws of physics, or perhaps part of an even higher level simulation? This raises the infinite regress problem. Who simulated the simulator? While challenging to answer, this open-endedness fosters endless contemplation. Furthermore, the idea of contacting the simulator has captivated imaginations, speculating on whether we could break out of the simulation, send messages to the higher reality, or even manipulate the code of our own existence. While captivating, simulation theory also faces significant challenges and counter-arguments. Firstly, it lacks direct empirical evidence. There's currently no definitive way to prove we are in a simulation, and any purported glitches in reality can often be explained by current scientific understanding or simply by the limits of our knowledge. Secondly, Occam's razor, a philosophical principle stating that the simplest explanation is usually the best, often weighs against it, positing a higher-level reality and a simulator adds layers of complexity without necessarily increasing explanatory power. Thirdly, the aforementioned infinite regress problem remains a conceptual hurdle. If our reality is a simulation, what is the reality of the simulator and the reality of their simulator? This chain of explanation can continue indefinitely, never reaching a truly fundamental base reality. Fourthly, there are philosophical challenges regarding the very definition of computation and reality within this framework. If everything is computation, what does that fundamentally mean for existence? Despite these challenges, the theory remains a powerful thought experiment, prompting us to critically examine our assumptions about the nature of reality and to explore the philosophical implications of our technological advancements. The connections between the digital universe hypothesis and our cosmic neuron analogy are deeply resonant, creating a multifaceted tapestry of possibility. If our universe is a colossal brain cell, it suggests a profound level of complexity and organization. This cosmic neuron could itself be part of a simulation, a single, incredibly sophisticated computational unit within the simulator's vast digital mind. Alternatively, the cosmic neuron could be the ultimate simulator, its thoughts and processes actively computing our reality into existence. In this view, the cosmic mind is the simulator, and our universe is a highly complex, self-aware program running within its vast computational network. Our thoughts then could be seen as subroutines or data patterns within the cosmic program, which is itself a program running within a higher reality. This creates a fascinating nested hierarchy of computation, information, and consciousness, where our existence is a conscious pattern within a cosmic program, which is itself a pattern in a larger computational framework. The profound connection between computation, information, and consciousness on a cosmic scale thus implies that awareness might be an inherent property of organized information, regardless of its physical instantiation, making our own existence a conscious data point in an infinitely vast, universal computation, contemplating the universe as a simulation, or as fundamentally digital information, can offer a unique sense of calm and profound philosophical reflection. The idea that reality is fundamentally orderly and logical, governed by precise rules like code, can be immensely reassuring, reducing the fear of cosmic chaos or arbitrary existence. It hints at a universe that is fundamentally rational and intelligible, even if its ultimate source remains hidden. The beauty of pure logic and mathematics as the ultimate language of reality can foster a sense of serene understanding and intellectual contentment. It implies that there might be a higher level of intelligence, purpose, or design inherent in the universe, the simulator, bringing a sense of meaning to existence that transcends random chance. Embracing the possibility of a reality that is fundamentally intelligible, even if its ultimate source is hidden, can foster a deep sense of peace. Our existence, then, as conscious patterns within this grand computational tapestry, is not arbitrary, but rather an intricate, meaningful part of an ongoing cosmic computation, inviting us to contemplate the profound beauty and inherent intelligibility of a universe made of information and code. A beautifully structured dream that we are all a part of, having gently journeyed through the mind-bending complexities of quantum mechanics, where reality seems to emerge from a mist of probabilities, and having contemplated the radical notion that existence might fundamentally be composed of information, or even a grand simulation, we now set our contemplative gaze upon an even more expansive and profoundly mysterious frontier, the hypothesis of the multiverse. What if our entire universe, with its billions of galaxies, its intricate laws, and its ceaseless flow of spacetime, is not the only reality? What if it is merely one bubble, one facet, one tiny part of an infinitely larger cosmic tapestry, a boundless collection of other universes, each perhaps with its own unique laws of physics, its own history, and its own inhabitants? Imagine a universe that is not just vast, but infinitely vast, constantly spawning new realities, each a unique expression of existence. This section invites us to calmly explore this mind-bending concept, to understand its scientific motivations and its various theoretical forms, and to contemplate the astonishing possibility that our reality might be merely one truth among infinite truths, fostering a deeper, more serene appreciation for the universe's hidden, boundless dimensions and the endless possibilities of existence at its core. The multiverse hypothesis is the theoretical proposition that our universe, the one we can observe and study, is just one among an immense, possibly infinite, number of other universes. These other universes may exist in different dimensions, branch off from our own, or simply exist as separate bubbles within a larger cosmic foam. The concept is not a mere product of science fiction. It arises from attempts to solve some of the deepest puzzles in modern physics and cosmology, offering elegant, albeit speculative, solutions to long-standing enigmas. It compels us to reevaluate our position in the cosmos, moving from being the sole universe to being but a single thread in an unimaginably vast cosmic fabric of realities. The very term multiverse encompasses a diverse array of theoretical models, each with its unique mechanisms for generating other universes and distinct implications for their properties and our connection to them. One of the most intuitive forms of the multiverse is often referred to as the level 1 multiverse or the infinite universe hypothesis. This model is a straightforward extension of our current understanding of cosmology. If the universe is indeed spatially infinite, and if matter and energy are distributed roughly uniformly throughout this infinite expanse, a principle known as cosmological inflation, then everything that can possibly happen, given the laws of physics, will happen, and in fact, will happen an infinite number of times. Imagine an infinitely large canvas filled randomly with paint. Eventually, every possible image will be painted somewhere on that canvas, an infinite number of times. In this scenario, there would be regions of space far beyond our observable horizon, the limit of what we can see due to the finite speed of light and the universe's age, that contain exact copies of our own solar system, exact copies of Earth, and even exact copies of you. Reading this script, experiencing this very moment. These other universes are not in separate dimensions. They are simply incredibly distant. Parts of the same universe too far for light or any signal to ever reach us. While simple, the implications are staggering. Every possible past, present, and future for you and for the universe is being played out an infinite number of times, somewhere out there in this boundless, ever-expanding cosmic expanse. Delving deeper, the level 2 multiverse, often called the bubble universes or eternal inflation hypothesis, arises directly from the most widely accepted models of the early universe. Cosmological inflation theory suggests that immediately after the Big Bang, the universe underwent an incredibly rapid exponential expansion. Eternal inflation takes this a step further, proposing that this rapid expansion didn't stop everywhere. Instead, it continues indefinitely in some regions, constantly spawning new bubble universes. Imagine a foam of soap bubbles, where each bubble is a new universe, constantly budding off from the inflating space. In this scenario, our Big Bang was just one tiny event in an endlessly inflating megaverse. Each of these new bubble universes could have its own unique Big Bang, its own set of fundamental physical constants, and even slightly different laws of physics. One universe might have stronger gravity, another might have a different speed of light, and yet another might be entirely devoid of stars or life. Our universe, in this view, is merely one unique bubble in a vast, endlessly diverse, and continuously created multiverse foam. This model offers a compelling solution to the fine-tuning problem, the perplexing observation that the laws and constants of our universe seem incredibly precise for life to exist. If there are infinite universes, each with slightly different constants, then it's no longer a miracle that our universe supports life. It's simply a statistical inevitability that some universe would have the right conditions, and we happen to live in it. The level 3 multiverse takes us back into the perplexing realm of quantum mechanics, specifically linking to the many worlds. Interpretation MWI, which we touched upon earlier in our contemplation of consciousness. This interpretation, proposed by Hugh Everett III, fundamentally asserts that there is no collapse of the wave function. Instead, every time a quantum measurement is made, or every time a quantum choice occurs, a probabilistic event at the subatomic level, the universe simply splits or branches into multiple parallel universes. Each branch represents a different possible outcome of that quantum event, and each outcome is realized in a separate, equally real universe. Imagine flipping a quantum coin. In one universe, it lands heads. In another, it lands tails. From our perspective, we only experience one outcome. But MWI suggests all possibilities are actualized across an ever-branching cosmic tree. This means that for every decision you make, for every interaction your body has, for every photon that hits your eye, the universe branches, creating infinite copies of you, each living out a different possible future. This is a truly radical concept of parallel realities, where every quantum possibility is concretized in its own universe. And the multiverse is an ever-expanding, branching tree of possibilities. It's an astonishing testament to the boundless potential inherent in quantum mechanics. Perhaps the most radical and abstract form of the multiverse is the Level 4 multiverse, often called the mathematical universe hypothesis, championed by cosmologist Max Tegmark. This hypothesis posits that all mathematically consistent structures are not just abstract concepts, but exist as real universes. In this view, our physical reality is merely one specific mathematical structure and any other mathematically consistent structure, no matter how bizarre or different its laws of physics might be, exists as an equally real, distinct universe. This means that reality, at its deepest core, is pure mathematics. The laws of physics are not descriptions of an external reality. They are the reality. This is the ultimate form of information, is reality, suggesting that mathematical existence equates to physical existence. This pushes the boundaries of what we traditionally consider reality, proposing a universe where every conceivable mathematical equation or logical structure plays itself out as a distinct, self-consistent cosmos. Other speculative multiverse theories include brane worlds arising from M-theory, string theory, suggesting our universe is a brane floating in a higher dimensional bulk space, with other branes representing other universes, and cyclical universes proposing that our universe undergoes endless cycles of expansion and contraction, with each big crunch leading to a new Big Bang, making the multiverse a temporal sequence of rebirths. The motivations for physicists to seriously consider the multiverse are deeply rooted in addressing some of the most profound puzzles in cosmology and quantum mechanics. The fine-tuning problem, as mentioned, is a primary driver. The fact that the fundamental physical constants of our universe, like the strength of gravity, the mass of electrons, or the cosmological constant, are incredibly precise for life to exist, seems to defy cosmic coincidence. If these values were even slightly different, stars wouldn't form, atoms wouldn't hold together, or the universe would have collapsed or expanded too quickly for complexity to emerge. If there are infinite universes, each with slightly different constants, then it's no longer a miracle that our universe supports life. It's simply a statistical inevitability that some universe would have the right conditions. And we happen to live in a THA form of the anthropic principle. Furthermore, the quantum measurement problem, which puzzles over why quantum wave functions collapse from possibilities to definite states, finds a direct solution in the many worlds interpretation, as it posits no collapse, just continuous branching, making all possibilities real. These compelling motivations push the multiverse from a mere fantastical notion to a serious, if still unproven, scientific hypothesis, offering elegant resolutions to long-standing cosmic enigmas. The implications of living in a multiverse are deeply profound, reshaping our understanding of identity, free will, and the ultimate nature of reality. If there are infinite copies of us across countless parallel universes, each living out different choices and experiencing different outcomes, does this dilute our sense of individuality? Which one is the real me? This concept challenges our traditional notions of singular identity, suggesting a collective or distributed self. The question of free will also becomes poignant. If every possible choice you could make is actualized in a different universe, as in MWI, does your choice truly matter? Or is your choice merely the act of your consciousness aligning with a particular branching reality? This can lead to a deterministic view where all possibilities are already fixed, just being played out. Ultimately, if the multiverse is real, it profoundly expands our understanding of ultimate reality. Our universe is no longer the totality of existence, but merely a single tiny component within an unimaginably vast, possibly infinite, cosmic landscape of realities. The unknowable nature of most other universes means that proving their existence empirically remains a formidable challenge. making the multiverse a realm of philosophical and theoretical exploration more than direct observation, connecting the vast concept of the multiverse to our cosmic neuron. Hypothesis creates an even more intricate and mind-bending tapestry of potential realities. If our universe is a single, colossal brain cell within a larger cosmic mind, then that larger cosmic brain might itself contain many such brain cells, each one a distinct universe within its vast consciousness. Could different thoughts or processes within the cosmic mind correspond to different bubble universes, each perhaps with varying physical laws and constants? Could the branching of the multiverse, as in the many worlds interpretation, be a microscopic level manifestation of the cosmic brain exploring or actualizing possibilities, its consciousness unfolding through an infinite array of realities? In this view, the cosmic neuron is not just a single brain, but a hypercomplex brain, its mind encompassing a multiverse of realities, each a distinct cognitive event within its vast awareness. Our thoughts, then, would be not just tiny patterns within our brains, but tiny nested universes within the cosmic mind, each a unique expression of its boundless computational and experiential capacity. This profound connection suggests that complexity and consciousness might not only emerge within single systems, but might also scale across nested hierarchies of existence, where one mind contains many universes, each potentially containing many minds. Contemplating the multiverse, especially through the serene lens of Sleepster, can lead to a profound sense of calm and wonder in infinite possibilities. The comfort in knowing that every possibility might be realized somewhere can reduce the anxiety of missed opportunities or wrong choices, suggesting that all paths exist in some form across the boundless cosmic landscape. It can reduce the fear of death or finality, hinting that consciousness may persist or branch into other realities, ensuring a continuity of experience beyond our current physical existence. The sheer awe of unimaginable vastness and boundless diversity within an infinite collection of universes is a powerful antidote to any sense of claustrophobia or limitation. The universe, seen as a boundless well of potential and existence, becomes an endless source of contemplation, inviting us to find peace in knowing that reality is far grander, more diverse, and more mysterious than previously conceived. This perspective gently lulls the mind into a state of acceptance, embracing the idea that existence is an infinitely unfolding story, with countless chapters playing out simultaneously across a cosmic landscape of infinite truths. Having gently journeyed through the mind-bending complexities of quantum mechanics, where particles dance as waves, and having contemplated the profound notions of reality as information, a grand simulation, or an infinite multiverse, we now arrive at the ultimate, most ambitious, and perhaps most deeply spiritual quest in all of physics and philosophy. We turn our contemplative gaze to the concept of the unified field, the elusive dream of discovering a single, overarching principle, a fundamental theory that could elegantly describe all of reality, from the smallest subatomic flicker to the grandest cosmic ballet of galaxies, and to unify all the forces of nature into one harmonious framework. Imagine the universe not as a collection of disparate phenomena governed by separate laws, but as a single, magnificent symphony arising from one singular resonant note, its deepest secret woven into a fundamental, unified tapestry. This section invites us to calmly explore this grand scientific and philosophical endeavor, to understand its historical roots, its current frontiers, and to contemplate the astonishing implications if humanity were ever to unveil reality's core principle, fostering a deeper, more serene appreciation for the universe's hidden fundamental unity and its boundless intelligibility. The dream of unification is as ancient as philosophy itself. Early Greek thinkers, like Thales, pondered if all matter might ultimately derive from a single fundamental substance, such as water, seeking a singular explanation for the diversity of the world. Centuries later, Isaac Newton achieved the first grand scientific unification, demonstrating that the laws governing the fall of an apple on Earth were precisely the same as those governing the majestic orbit of planets around the Sun. He unified terrestrial and celestial mechanics under the single elegant law of universal gravitation, revealing a profound underlying order. The 19th century witnessed another monumental unification. James Clerk Maxwell, through his brilliant work, showed that electricity and magnetism were not separate phenomena, but two facets of a single fundamental force, electromagnetism, and that light itself was an electromagnetic wave. This revealed an astonishing interconnectedness in apparently disparate phenomena. These historical triumphs inspired the greatest minds to believe that nature, despite its apparent complexity, is ultimately simple at its core, hinting at a single, elegant truth underpinning all existence. This vision culminated in Albert Einstein's lifelong, passionate quest for a unified field theory, a single, all-encompassing set of equations that would describe all the fundamental forces of nature. While Einstein succeeded in unifying space, time, and gravity into his general theory of relativity, he ultimately did not achieve his dream of incorporating electromagnetism, let alone the other forces, into a single framework. His failure merely underscored the immense difficulty and the profound depth of this ultimate scientific puzzle. Today, our understanding of the universe is built upon four fundamental forces that govern all interactions. The strong nuclear force is the most powerful force in the universe, but it acts only over incredibly short distances, binding quarks together to form protons and neutrons, and holding atomic nuclei together against the immense repulsive forces between positively charged protons. It is the glue of the nucleus. The weak nuclear force is responsible for certain types of radioactive decay, enabling processes like nuclear fusion in stars. It acts over even shorter distances than the strong force, and it is crucial for transforming one type of subatomic particle into another. The electromagnetic force governs the interactions between electrically charged particles. It is responsible for all of chemistry, light, electricity, magnetism, and the very structure of atoms and molecules. It acts over infinite distances, though its strength diminishes with distance. The gravitational force, the weakest but most pervasive force, attracts objects with mass or energy. It acts over infinite distances and is responsible for the formation of stars, planets, galaxies, and the large-scale structure of the universe. Each of these forces operates under its own set of rules and strengths, yet the dream of unification seeks to show them as different manifestations of a single underlying fundamental force. A single symphony played with four distinct instruments, our current most successful model for describing the universe's fundamental constituents and their interactions is the standard model of particle physics. This extraordinary theory successfully describes three of the four fundamental forces, the strong, weak, and electromagnetic forces, and classifies all known fundamental particles: the quarks, which make up protons and neutrons; the leptons, like electrons and neutrinos; and the bosons, which are the force-carrying particles, such as photons for the electromagnetic force, gluons for the strong force, and WNZ bosons for the weak force. The Standard Model is a triumph of human intellect and experimentation, providing incredibly precise predictions that have been repeatedly confirmed by particle accelerators like the Large Hadron Collider. Its crowning achievement was the discovery of the Higgs boson in 2012, the particle associated with the Higgs field, which gives mass to other fundamental particles. Despite its phenomenal success and predictive power, the Standard Model remains an incomplete picture of reality. Crucially, it does not include gravity, the most familiar force. It also does not explain the existence of dark matter or dark energy, which constitute the vast majority of the universe's mass and energy. Nor does it explain why fundamental particles have the specific masses they do, or why there are three generations of quarks and leptons. It is an incredibly powerful but ultimately unfinished symphony, leaving physicists in pursuit of a grander, more comprehensive theory. The ultimate quest in modern physics is for a theory of quantum gravity, a framework that would successfully unify general relativity, which describes gravity on large scales, with quantum mechanics, which describes reality at tiny scales. These two pillars of 20th century physics are incredibly successful in their respective domains, but are fundamentally incompatible with each other, leading to contradictions when attempting to describe phenomena like the Big Bang or the interior of a black hole. Numerous theoretical avenues are being explored to achieve this ultimate unification. One prominent approach is loop quantum gravity (LQG), which proposes that space-time itself is not a continuous smooth background, but rather is fundamentally quantized, composed of discrete, tiny loops or nodes of space and time at the Planck scale. In LQG, space and time are not continuous, but woven from a discrete quantum fabric, changing our understanding of reality's very texture. Another, perhaps more widely known, contender is string theory, and its overarching framework, M-theory. String theory proposes that the fundamental constituents of reality are not point-like particles, but rather incredibly tiny, one-dimensional vibrating strings. The different ways these strings vibrate determine the properties of the particles they represent. For example, one vibration might be an electron, another a photon. String theory naturally incorporates gravity and aims to unify all four fundamental forces within a single framework. It also requires the existence of extra spatial dimensions beyond the three we perceive, which are theorized to be compactified or curled up at incredibly small scales. M-theory is an even more ambitious framework that aims to unify various consistent string theories, suggesting an even more fundamental reality operating in 11 dimensions. If these theories are correct, reality at its most fundamental level is not particles or fields, but vibrations in higher dimensions, or discrete chunks of spacetime, fundamentally redefining the very stuff of existence beyond strictly physical. Unification, the concept of a unified field, also resonates with the idea of information as the core of reality, which we explored previously. If a grand unified theory were to describe all forces and particles, what would that ultimate field itself be made of? Could it be fundamentally information, a cosmic code from which all physical manifestations emerge? Wheeler's it from bit notion that every physical it arises from a binary bit of information would find its ultimate expression in such a unified informational field. This suggests that the universe's most fundamental principle might be computational or informational. In nature, with all physical laws being algorithms and all phenomena being data processing. This naturally leads back to the role of consciousness. If information is fundamental, and consciousness is the highest form of information processing known to us, could a unified field theory ultimately reveal how consciousness emerges from, or is even fundamental to, this single core principle? Perhaps consciousness is the ultimate unified field, or its highest emergent property. The philosophical implications of achieving unification are immense, leading to a profound sense of cosmic harmony and intellectual serenity. Discovering a single, elegant underlying principle for all reality would provide an unparalleled sense of completeness and understanding, revealing the universe to be ultimately intelligible, even if its deepest laws are incredibly complex. It would confirm a profound sense of cosmic harmony, demonstrating that all phenomena, from the quiet growth of a plant to the explosive birth of a supernova, are interconnected by a single underlying truth. This quest embodies humanity's deepest aspirations for knowledge and meaning. It finds profound resonance with the cosmic neuron hypothesis. If the universe is a brain cell, The unified field would be the fundamental principle of that brain. Cell's existence, its very operating system or source code. Could the cosmic mind's thoughts and experiences be manifestations of this unified field? Its internal dynamics being the unfolding of this singular principle. Perhaps the ultimate unified theory would be the grammar or logic of the cosmic brain itself, describing how its vast elements work together to produce cosmic consciousness. However, the pursuit of this unified field remains an unfinished symphony. Despite immense intellectual effort, a single universally accepted theory of quantum gravity remains elusive. There are still many theoretical hurdles, experimental challenges, and fundamental questions that lie beyond our current grasp. Yet, the beauty lies not just in the potential destination, but in the continuous journey itself, the relentless human quest to push the boundaries of knowledge, to refine our understanding, and to seek the ultimate coherence of existence. This enduring pursuit, even in the face of profound difficulty, is a testament to the insatiable curiosity of the human mind, its capacity for abstract thought, and its yearning for universal truth. The beauty lies in the ongoing search, the continuous pushing of boundaries, and the humility of recognizing that the universe's deepest secrets are meticulously guarded. Finding peace in this grand, ongoing quest, accepting that the universe is vast and its ultimate truth might forever unfold, allows our minds to rest gently in the boundless potential of the unknown. We are participants in this grand cosmic puzzle, seeking a singular, unifying melody in the universe's infinite song.